The modern quantum computing industry is heavily built on maintaining highly fragile transmon circuits at the microscopic level. Keeping those subatomic states stable requires massive infrastructure, specifically millikelvin cryogenic cooling systems designed to hold hardware near absolute zero. But consider an alternative approach: processing quantum superpositions using a macro-scale analog mechanical system operating completely at room temperature. Escaping the cryogenic chamber requires abandoning subatomic physics entirely. We must replace particle states with a physicalized electromechanical probability matrix. These handwritten notes provide the architectural blueprint for exactly that kind of non-standard computing structure. The engineering challenge is translating this theoretical framework into a massive operational computing floor spanning exactly 250 square feet. Building this facility requires solving three immediate architectural hurdles: formulating the logic gate, constructing the magnetic layer, and managing catastrophic thermal loads. Scaling this massive design forces continuous quantum wave functions to be processed entirely by discrete, heavy, room-temperature industrial machinery. Traditional computer science relies on strict binary systems, using the absolute states of ones and zeros. Here, the author designs a core logic unit to hold superpositions, the Qbin. The vertical fractional notation you see, 1 over 0, 0 over 1, records superimposed states mathematically. Instead of an electrical gate sitting definitively open or closed, the Qbin maintains both potential values simultaneously in this fraction form. This text introduces a reverse binary probability matrix. By applying positive and negative degrees of power to these input-output fractions, the system calculates specific quantum numerical values. Standard cryogenic qubits exploit highly unpredictable atomic behavior. The Qbin explicitly maps the probability of states as a fixed mathematical matrix. This mathematical shift turns quantum superposition from an elusive subatomic phenomenon into a predictable macroscale calculation. Physically recording these fractional probability matrices at room temperature poses an immediate hardware challenge. The notes detail the physical medium, a grit-based punch card system printed directly onto magnetized paper. To read the data, the hardware relies on Hall effect sensors. Hall effect sensors sweep over the magnetic grid, detecting continuous fractional variations in the magnetic field rather than discrete binary clicks. Interpreting these continuous magnetic variations captures a physical spheric representation of a quantum state, modeling the same function as a standard Bloch sphere. By utilizing continuous magnetic polarization, the hardware effectively creates a room temperature physical analog for quantum wave collapse. Networking thousands of these sensor nodes is necessary to execute complex logic operations across a 250 square foot floor. While binary logic chains link linearly, this diagram maps out a quantum chain utilizing specific multi-node cross formations. These physical cross shapes simulate entanglement algorithms. They geometrically interlock the probability outcomes of adjacent qubins, so one node directly influences another. Scaling this requires tiling millions of these interlocking magnetic crossgates across the facility floor. In this massive analog architecture, complex algorithms are solved through spatial geometry and sheer grid density, entirely bypassing unpredictable subatomic entanglement. Scaling a high-density, rapidly fluctuating electromechanical grid introduces severe friction and extreme heat generation. Rapidly flipping the magnetic polarity of millions of high-density electromagnets across the facility floor induces massive Joule heating. This heat threatens the system due to the Curie temperature limit of the magnetic punch card material. If the ambient heat of the 250 square foot grid exceeds the Curie limit, the magnetic paper completely loses its polarization. The analog superposition data wipes instantly. Preventing this data loss requires routing heavy liquid cooling infrastructure directly through the logic arrays. The 250 square foot footprint serves as the thermal floor for the system, the absolute minimum area needed to physically dissipate the heat generated by simulated quantum algorithms. We have drafted a room temperature continuous probability grid kept stable by massive thermal management infrastructure. We translated fractional mathematics into a giant electromechanical Leviathan. The original notes outline a specific philosophy justifying this analog approach. An airplane does not mimic a horse's galloping legs to travel quickly. Similarly, This analog machine does not need to mimic microscopic subatomic particles to process quantum logic. The Malpani framework presents a divergent structural architecture to arrive at the exact same computational destination. While standard processors command the microscopic realm, this blueprint proves quantum states can be computed through brute force, room temperature, macroscale engineering.